Okay, so in this particular video, we'll attack another velocity versus time graph here, which is different than the other videos. But at the end of the day, if you've seen the other velocity versus time graph, there are important information that you should be able to extract looking at a velocity versus time graph. One, being the slope of the velocity versus time graph. So keep in mind the slope of a velocity versus time graph is your acceleration. Two, the area beneath the velocity versus time graph that touches the horizontal axis is your displacement, which could also be your distance if you're just looking at the absolute value of these areas. Okay, so keep those statements in mind. If you need to, rewind the video and write down what I just said. All right, so let's go ahead and attack A, B, C, D, E, F, and G. All right, but before we do that, I'd like to go ahead and encourage you to visualize motion as you look at velocity versus time graph. Understand what's going on. That way, as you get answers that make sense and is reasonable. All right. So here in this particular graph, I noticed that time is equal to 0. The object's velocity is -4 meters per second to start, which implied that it is moving leftward to start. And then at 2 seconds, if I go across to the vertical axis here, I notice that it is at 0. So what does that mean? Initially it's moving leftward and then somehow it came to a stop at 2 seconds. But then I noticed that after 2 seconds, all of my velocity values are positive, which suggests that the object turned around. And then from 3 to 5 seconds, I notice here it's still moving, but it's moving at a constant rate, with the rate here being 2 meters per second. So once it turns around and it speeds up in the opposite direction, after it got to 2 meters per second, it kept that speed constant for a couple of seconds based on this graph. Okay. So the arrows that are about to come up is just to help you visualize. Here, I have an arrow pointing towards the left because my initial velocity is -4 meters per second. These are just to help you visualize. And then as time progresses, the length of these arrows or the magnitude of these arrows keep getting shorter. Well, they're getting shorter because the object eventually comes to a stop at 2 seconds. Again, at 2 seconds, if you go across, the velocity is 0. And then what happens after 2 seconds? Well, it turns around. How do I know that? Because after 2 seconds, all of my velocity, if you trace it, it's all positive, okay? Or it's just above the t-axis, which implies that it's positive. So therefore, the object turns around. It turns around and it picks up speed. But after 3 seconds, though, after 3 seconds, from 3 to 5 seconds, it keeps the same constant velocity. Well, how do I know that? Because the slope here is 0. And if the slope of this graph here, as I said earlier, is your acceleration, if the slope is 0, therefore it implies acceleration is 0, which implies that the object now just moves at a constant rate, whatever rate that is. So at 4 seconds, it is now 2 meters per second. Let's say, for example, at 4.2 seconds, you go across, it's still 2 meters per second. At 4.5, you go across, it's still 2 meters per second. At 5 seconds, it's still 2 meters per second. So it remains a constant velocity. Okay, so the arrows that are coming up now are all the same size. They're all the same size because it sped up for a little bit and then it just kept that speed of 2 meters per second for a while. Okay, all right, so that's the visual for this particular graph. So let's knock out part A, B, and C. Part A asks us to find the average acceleration for the first 3 seconds. The first 3 seconds would imply that, watch my cursor on the graph, I would start there as 3 seconds and I would go all the way up. Okay, so 3 seconds along the horizontal axis, that's 1 second, that's 2 seconds, that's 3 seconds. And I go all the way up to where it touches the graph, the green graph. And if I go all the way across, that is a velocity of 2 meters per second. So to find average acceleration, I need the change in velocity over the change in time. Here, I've just chosen to go from 0 seconds to 3 seconds because that's what it's specified. Here, change in velocity over change in time. So here I've circled my initial velocity is -4, and then my final velocity is a +2. So therefore, I can just plug it into the average acceleration function, which is VF minus VI. My VF here is 2 meters per second because the graph said so, minus my initial is a -4. So you notice here I've used parentheses just to, as good habits. So the function itself calls for a negative sign, but the value of VI itself is also a negative. So I encourage you to use parentheses. This way you don't mess up on the algebra stuff, okay? All right, so here we have 2 minus a -4, a negative, and a negative makes a positive. So here we have 2 plus 4. So therefore the numerator becomes 6, and then the denominator is just 3 seconds because it wants us to go for the first 3 seconds. 6 divided by 3 is 2. Here I've included the direction because it asks for average acceleration, and acceleration is a vector, so the answer would be a positive 2 meters per second squared, which makes sense. If you look at the graph from 0 to 3 seconds, this green line here, this green diagonal has a positive slope. Well, what is the slope of this line? It's 2 for every second. So if you watch my cursor, every 1 second that I go over, it goes up 2. Every 1 second I go over, it goes up 2. So every 1 second over, my velocity increases by 2. So therefore, the acceleration is 2 meters per second, and it's positive because the slope is a positive quantity. All right, that's that. Now let's go ahead and knock out part B. Okay, part B asks us to find the total distance traveled during the first 5 seconds. So pretty much the whole entire graph that's shown here. Okay, so the graph kind of cuts off at 5. It doesn't really matter. You just have to go with whatever's given to you, on homework or on assessment. All right. So therefore, to find total distance, the easiest way to do it is just to find the area. While the area represents displacement, distance is the absolute value of your displacement because it is a scalar. So whether you're moving left or right, it doesn't really matter. You're just counting every step. So distance, you count every step that's taken, whether it's left or right, aka the absolute value. So I'm going to find the area of each of these segments. Again, if you have to make sure you shape the area correctly. You start from the line and you go all the way to the t-axis. So, or you go all the way from the line, you go down to the t-axis. You have to make sure you're able to You have to make sure you're able to shade these areas correctly. If not, your values will be all jacked up. Okay. So let's go ahead and knock out the first area. The first area is just a right triangle, which is 1/2 times base times height. So if you look at the yellow triangle here, my base is 2 because I'm going to go from 1 to 2 seconds, and then it's going to go 1, 2, 3, and 4 down. Okay, so therefore the first area here I call area 1. It's 1/2 times base times height. My base is 2, and my run or my height here is -4 because it's beneath the t-axis. So here my displacement is -4. Okay, it's -4 because the area that's shaded is beneath the t-axis. So it's that easy. If it's below, it's negative. It's above the t-axis, it's all positive. Okay. So I know that the object moves leftward 4 meters. Okay, during the first 2 seconds. Now let's go ahead and find the area of this blue triangle. This is also a right triangle. So therefore, we can just apply 1/2 base times height again. But you got to make sure you count carefully. The base here is just 1. From 2 to 3 is 1, and I go all the way up. That's 1. That's 2 based on the graph. So my base is 1 and my height is 2. And that's where the 1 and the 2 comes from. So 1/2 times base, which is 1, times the height, which is 2. And if you punch in your calculator or just do basic math, that is 1 meters. Okay. And then let's go ahead and find the third area, which is in purple here or pinkish. Here, this is just a rectangle. So therefore, to find the area is just base times height. My base here is 1 and 2. So the difference from 3 to 5 is 2. And I want to go up 2. So 2 times 2 is 4. So that is the area. Okay. Now, it's important to pay attention here. Hopefully you're not watching this too fast. It asks for total distance, and total distance is the absolute value of your displacement. So why I found that the area for A1 is -4 meters, I need the absolute value. So it walked leftward 4 meters, but I don't care for the direction. I just need the fact that it walked 4 meters. So you notice here in my total distance, I put A1 plus A2 plus A3. But for A1, I use a positive value because I'm looking at distance, and distance is a scalar. So here, it walked 4 to the left, but I don't care about the direction. So it walked 4 steps, and then it turned around, it walked another step, and then it walked another 4 steps. So the total amount of meters that it walked is 9 meters, okay? So be careful with displacement versus distance. For distance, just add everything. There is no such thing as negative distance. So 4 plus 1 plus 4 gives us an answer of 9. So that would be our answer. No direction needed because distance, again, is a scalar quantity. Now, if you wanted to, you can actually apply a physics function to prove that it does come out to be 9, right? So can we do the first triangle here? I'll call that my displacement 1. Well, I can use my kinematics equation. So I'll use delta x here. I just denote as 1 because that is my first segment. VIT plus 1/2 AT squared. But if I do this yellow shaded area, my initial velocity here is -4 and my time is 2 because, again, if you look at the axis carefully, it goes 1 and 2 seconds and my initial velocity here is -4. We already know our acceleration previously because we already calculate that, and our acceleration here is a positive 2 meters per second squared. So it really becomes a plug and chug. VI is -4. Time here is 2 because the yellow area occupies 2 seconds. 1/2 times 2 for A, and then times 2 for the T, and then we'll square that. And if you simplify all of that, you get -4 meters, which is consistent with just finding the area of the shaded region. Now let's go ahead and find delta x2. Delta x2 is this little, blue triangle, right? So therefore, let's use the same kinematics equation. Delta x2 is VIT plus 1/2 AT squared. But if you start at 2 seconds, your initial velocity is not -4 anymore. As a matter of fact, if you trace the graph to 2 seconds and you go all the way across, your velocity here is 0, even though there's no 0 on the graph. It is at the origin. So therefore, its initial velocity is 0. So you have to pay attention to time frames and intervals, okay? So here I'm going to cross out VIT because I'm doing the second segment, and the second segment for the blue triangle starts at 2 seconds, and at 2 seconds the velocity is 0. So that's my initial, which I'll just cross out. So therefore, the only thing that's left is 1/2 AT squared. Again, we know A is 2. Here time is just 1 second because from 2 to 3 seconds is just 1 second. So if you punch this in your calculator, it'll be just 1 meter, okay? Which is, again, it's what we got by finding the area. Let's go ahead and do displacement 3, okay? Delta x3 here, we already know the answer was a +4, right? Because it's above the t-axis, but let's use physics here. Delta x3 is VIT plus 1/2 AT squared. Well, if you look at the graph here from 3 to 5 seconds, if you heard me earlier, the slope here is flat. There is no slope, which implies that the acceleration is 0. Okay, so it's moving at a constant velocity, which suggests that it's not speeding up nor slowing down. Therefore, in physics, we say that it is moving at a constant rate. What rate? In this graph, it's moving at a constant 2 meters per second, 2 meters per second, 2 meters per second. All right, so therefore, because acceleration is 0, I'm going to cross out the 1/2 AT squared. And therefore, really, my VI here now is 2. So you notice here, as I do these different parts, different segments, I call it, my VI changes. My VI changes because I'm starting at a different time. So for this third segment, my initial time here is 3 seconds. Well, at 3 seconds, I go all the way up to the graph. I go all the way across. The velocity is 2. So it's important that you understand that as you chunk up problems, your VI could change. In this case, it does change. Okay. So my VI here is 2. The change in time here is 2 because from 3 to 5 is 2. So 2 times 2 is 4. We got the same values here, -4 meters, 1 meter, and 4 meters, just like we did using the concept of finding the area beneath the velocity time graph. All right, so that's that. So that's just to help you out. So for part B, again, if it asks you to find distance, you don't care about the negative sign. You just go 4 plus 1 plus 4, which is 9 meters. Okay, let's do part C. Part C asks us to find the average speed during the first 5 seconds. Well, average speed by definition is just distance over time. Well, we already found our distance in part B. The total distance for the first 5 seconds is 9 meters, and then the time is just 5 seconds. So 9 divided by 5 is just 1.8 meters per second. Here, average speed is a scalar, so you don't need to include any sort of direction. All right. So as you are able to find areas and know how to interpret that, finding average speed and average velocity becomes really, really easy, as long as you apply physics properly. All right, let's do part D and E. Okay. For part D, it asks us to find the average velocity during the first 5 seconds. Okay. And E wants us to find the runner's instantaneous velocity at 1.25 seconds. Well, let's do part D real quick. Just to recap, these shaded areas that I carry over here, yellow, blue, and purple, we all know the answer to this, okay? The answer to the area here in yellow is -4, because that's displacement. It moved 4 meters to the left, aka -4 meters. Here, the blue area was 1, the purple area was 4, but here it asks for average velocity. Well, average velocity is not the same as average speed when an object turns or changes direction, which it does in this one, okay? So again, it was moving leftward until 2 seconds, and at 2 seconds it actually stops and then changes direction and starts moving to the right. The fact that it changes direction tells you that average velocity and average speed are no longer the same magnitude. So you have to make sure you apply physics function properly. So to find average velocity, you need displacement over time. Well, displacement is a vector, so here's -4, here's a +1, and here's a +4. Well, -4 is going to cancel out with +4. So really, my displacement is 1 meter to the right. So even though the car or the object or the particle moved leftward, at the end of 5 seconds, it is 1 meter to the right of where it started, okay? So therefore, I just plug values in here for you. Since it asks for displacement, you notice here I include the negative sign because displacement is a vector. So therefore, I need to include the fact that it was moving leftward to begin with. It was moving leftward 4 meters. It stopped, changed direction, moved 1 meter as it accelerated, and then it kept going at a constant rate of 2 meters per second for 2 seconds and cover another 4 meters. So basic math tells you -4 and 4 cancels out. So it leaves us with just 1 over 5. So 1 over 5 is 0.2 meters per second. And here I've chosen to include the direction for you because it asks for average velocity, and average velocity is a vector. Okay, so that's our answer, plus 0.2 meters per second. Now, let's do part E. Okay. Oh, by the way, I want to point out, if you didn't see my previous video, I wanted to point out this particular function here. V average is equal to Vf plus Vi divided by 2. It's only good when acceleration is constant. The fact that part D asks us for the first 5 seconds suggests that we have the first segment, the acceleration is a positive 2 meters per second square, but then from 3 to 5 seconds, the acceleration is 0. So you have 2 different accelerations. So therefore, you cannot use this function here, okay? You can only use this function per segment. Like you can use it from, let's say from 0 to 3 seconds because the acceleration is positive 2. You can use it by itself from 3 to 5, but you cannot use it from 0 to 5 because acceleration changes. So the acceleration for the first 3 seconds here was 2 meters per second square, and all of a sudden the acceleration from 3 to 5 is 0. The value changed, so you cannot just group things together like that. So it's important that you understand how to apply this function. You can apply this function correctly per segment, all right? So careful on how to do this. Sometimes kids just want to do Vf plus Vi divided by 2, even though, you know, it's 2 different slopes or 2 different type of slopes here. All right, let's do part E. It says, what is the runner's instantaneous velocity at 1.2 seconds? So to find instantaneous velocity really is the same as asking you to find Vf. Vf is at plus Vi. We know our acceleration is 2 because the time here is 1.25, which falls between 0 to 2 seconds. So 1.25 is about right here on the graph, which falls in this yellow region, which is part of this slope. Okay, so I know I can use acceleration as 2 meters per second squared because it's part of that slope. Here my time is 1.25 because I'm going to start at 0 second. But if I start at 0 second, my initial velocity here for this graph is -4 meters per second. So it's important that you just don't make false assumptions, okay? Read the graph and make sure you go with the information presented to you. Sometimes kids cross out Vi thinking it's 0 and it is not for this graph. At times you go to 0 for this graph, you go all the way down, the initial velocity is -4 meters per second. So it's important that you plug in proper values and not make false assumptions. All right, so if you finish your calculator work, okay. So here we have 2 times 1.25, which gives us 2.5, and then I'm going to carry that -4 meters per second down. So if you simplify that, you get an answer of -1.5 meters per second, which I think makes sense. Again, if you go up to the graph, 1.25 seconds about right here. If you go down and you trace it across, I know my value here has to be in between -1 and -2, and it happens to be -1.5, which is reasonable. It makes sense. So hopefully, as you practice, your calculator work is solid, okay? But you should be able to ask yourself, does it make sense? I want to say that it does make sense because it does fit with what I should expect, or about what should I expect. All right, let's go ahead and do F and G. Part F asks you, what is the runner's velocity at 2.7 seconds? So here's 2 seconds, and then here's about 2.7, where my cursor is tracing out. Again, about there. If I go up, you know, that's where the green line is, and I go all the way across, I know I should get a value less than 2, but bigger than 1, okay? Because that's what the graph interval is. All right, so let's do it and make sure our answer makes sense. Well, for this one, you can do it using 2 different approaches. I can go from 0 second to 2.7 seconds because it asks us to find the final velocity at 2.7 seconds. Okay, so I can use Vf equals at plus Vi again. But if I go from 0 second to 2.7 seconds, my A is still positive 2 because that's what the slope is at this point. Okay, my time here is 2.7 seconds because from 0 to 2.7 is a difference of 2.7 seconds. And if I start at 0 second though, the graph again indicates that my initial velocity is -4. So for Vi, I'm going to put in a -4. if you simplify this stuff, 2 times 2.7 is 5.4. You're going to add a -4 because that's your initial velocity. And if you do this, you should get a value of 1.4. And it's plus here because 5.4 is bigger than -4. So which makes sense. Again, on the graph, if I go from 2 to about 2.7, eyeballing it, I go up. I know that the value is less than 2 but bigger than 1. And 1.4 fits that, approximation, okay? So here, I include the plus sign because it asks for instantaneous velocity, which is a vector. So that's my answer, part F. However, I would prefer to do, if you look at stuff carefully, instead of going from 0 to 2.7, if I was doing this, I actually would go from 2 to 3 seconds, okay? From 2 to 2.7 seconds. The reason I want to go from 2 to 2.7 seconds is because if I look at the graph, at 2 seconds, the object's velocity came to a stop. So at 2 seconds, its instantaneous velocity is 0. Now, why would I want to choose 2 seconds and go to 2.7 seconds? Because it just makes my life easier. And there's less mistakes that can happen. Here, Vf is equal to at plus vi. My acceleration is 2, except my time here is only 0.7. Okay? It's 0.7 because 2.7 minus 2 is 0.7. Now, what happened to vi though? Well, if you heard me earlier, I wanted to start at 2 seconds because I know at 2 seconds the velocity is 0. So that's my initial condition. Well, if I start at 2, the vi does not exist because it's momentarily at rest. So really, all I have to do is punch in 2 times 0.7 and I will get the same answer as the previous strategy. Okay, so I like being able to look at a graph and then pick the better choice. There's no wrong choice, you just pick the better choice. I would start at 2 seconds only because I know that at 2 seconds, the velocity on the graph is 0 meters per second. It just makes you work a little shorter, that's all. All right, so that's that. As you can see, it gives us the same answer. All right, now let's do part G. Now, if you haven't been listening throughout this whole video, then you should rewind and listen. I don't want to be mean here, but you should hopefully listen well. The average acceleration is the slope of a velocity time graph. Well, if you looked at the interval 3 to 5 seconds, according to this graph here, if you go from 3 to 5 seconds, if you look all the way up, as I stated before, this segment here is flat. Because it's flat, it's horizontally flat, there is no slope. Well, what does that tell you? Acceleration is the slope of a velocity versus time graph. From 3 to 5 seconds, the slope is 0. So therefore, it is safe to say and correct to say that the average acceleration is just 0 because there's no slope. And that's it. There's no really work to be done, okay? I mean, you could plug in Vf minus Vi, which is 2 minus 2, and 2 minus 2 is 0, divided by any time interval is 0. But I encourage you just look at shapes and then know what the outcome is just by looking at it. So for this one, I'm not doing any math. I'm just going to say that that slope is flat. Because it's flat, my acceleration is 0. So that's that for this video, okay? I hope that helps. Stay nerdy. Don't be whack.